Okay, let's look at the theorem. This theorem says that for any square matrix A, the determinant of its transpose is the same as the determinant of A. In other words, if we take the determinant of A or we take the determinant of A transpose, we will get the same result. Here is the proof. The proof of this theorem will be only done by two matrices, because for bigger matrices we will not prove here. So let's have a proof of this statement by using the 2 by 2 matrices. Since any 2 by 2 matrix can be represented in this way, so if this is the 2 by 2 matrix, then its transpose will be obtained by making rows into columns. For example, this is the row, so here it is the column. This is another row, here it is the column. So the transpose can be obtained by converting the rows into columns. So this is the transpose. So let's find the determinant of both matrices explicitly. We have to check that whether the transpose of this matrix and the transpose of this matrix are equal or not. So let's calculate them explicitly. The determinant of A is just the product of these two entries, which is AD here, minus the product of these two entries, which is CD here. BC here, right? Now let's look at the determinant of A transpose. The determinant of A transpose is the product of these two guys, A times D, which is here, A times D, minus the product of these two, which is C times B, and which is the same as AD minus BC. Since the transpose of both, since the determinant of both A and A transpose are equal, so the theorem is proved. Let's do an example. We have to verify that the determinant of this matrix and its transpose are equal. So let's first find the determinant of this matrix. So suppose that this matrix is A, then the determinant of A can be obtained by expanding along the first row. You can check, this is the first row. In the first row we have 1, 0 and 2. So I will write 1, 0 and 2. Then I will write -1 everywhere. You can check -1 everywhere. Then I will write -1 to the power something. What is here? What should be written here? Since this 1 is in the first row and the first column, so I will write 1 plus 1 on the power. Since this 0 is in the first row and the second column, so I will write its power to be 1 plus 2 here. This 2 is in the first row and the third column, so 1 plus 3 is the power. So I have written 1 plus 3 in the power of -1 here. Now, in these vacant places, I will put the determinant of the submatrix. For example, for this one, I will cross this column and this row. I will end up with this matrix. So the determinant of this submatrix is 5 times 4 minus 1 times 1. Okay. Similarly, for this 0, I will have to skip this and this. I have got the submatrix 3, 1, 2, 5, whose determinant is here, 3 times 5 minus 2 times 1. And similarly, when I will go to the the last entry, which is 2, I will skip this and I will skip this. And then I will write the determinant of this submatrix, which is 3 times 1 and 2 times 4, which is written here. Now I will just calculate these things. You can check that this is 1 and this is 20 minus 1. This is 0. I have not written. This is 2 times 3 minus 8. If I calculate it more, I will get 9 as a result. Now let's calculate the determinant of A transpose. This is the determinant. You can check. It is the matrix. If I convert every row into column, for example, this is the row 102, I have made it a column. Similarly, 341 is a row. I have made it a column, the next column. And similarly, 215 is another row. I have made it the last column. Now I have to find this determinant. Since you know that in order to find the determinant, we can expand the determinant by any row or by any column. And we have studied that we will expand by the column or the row which has more number of zeros. Since the first column has more number of zeros, it has 1 0, I will expand this determinant by using the first column. So if I expand this determinant using the first column, so I will first write the first column entries which are 1, 0 and 2. So these are the 3 entries of the first column. Then I will write the minors. First of all, I will write -1 everywhere. You can check, I have written -1 everywhere. Then I will count where these entries are lying. Since 1 is lying on the first row and the first column, I will write 1 plus 1 here. Right? I will write 1 plus 1. Since this 0 is lying on the second row and the first column, I will write 2 plus 1. Since this 2 is lying on the third row and the first column, so I will write 3 plus 1. And then I will write the subdeterminant of the submatrices. Since for this entry, I will skip this and this, the determinant of this will be written here, which is 4 times 5 -1 times 1. For this 0, I will skip this and this. I will write the determinant of the submatrix, which is 3, 2, 1, 5. You can see, which is 3 times 5 -2 times 1. Similarly, for the last entry, I will skip this and I will skip this. This is left. I will write the determinant of this, which is here. You can check. Now I will calculate all of these things. After calculation, you can check. Everything is very easy. And we have got the same result. Here, the result was 9. Similarly, here, the result is also 9. So this theorem is verified.